trends in power and energy in integrated circuit. Am I, guys, am I audible?
Yes, ma'am.
So the next things, I mean, with respect to computer architecture design, is are the computer designer facing is deep power. Okay, because like the power has to be brought in and it is distributed around the chip. So we have like when you just go with the modern processor, you have hundreds of pins and so many interconnected layers will be there for power and ground. So it has to be clearly done. It has to be brought in and it has to be distributed accordingly. And the second thing is, so distributing is one thing, and the power is dissipated as heat and must be removed. This is the two important things that has to be considered with respect to power. So how you need to distribute the power, and once it has been distributed, definitely there will be a dissipation, heat dissipation from it there, and how we need to remove that. So these two things has to be uh, carried out in a good manner. So when I write with respect to power, there are three primary concerns from the designer viewpoint. Okay, what is that is the first one, maximum power a processor ever requires. First, we need to, I mean, because it doesn't know, assume that we have so many components, so 3 volt to 5 volt, it may varies, right? So we have to be very thorough with the voltage that it requires for any specific things has to get activated. Okay, so that is very very important. Suppose if your processor is attempt to draw more power than the power supply systems, so what will happen? So definitely there will be a voltage drop and it may cause the device to malfunctions. So this has to be accurate. So correct operations. So how much it requires has to be forecasted or predicted correctly. So then only right this sort of voltage drops can be reduced. Otherwise, it may lead to malfunctions. But nowadays, like you have in case of modern processors, what I mean now current processors and all, they have something called voltage indexing methods. Some voltage indexing methods will be there. So this is taking care of it. If suppose if found if there is any voltage drop or something is happening, so it may slow down it. It will slow down the processor and accordingly it will start regulate. So this will helps it out. Okay. So they have provided so many. I mean, the computer designers provided so many things. So of that one thing is this voltage indexing method. So this voltage drops can be avoided with the help of that. Okay. The next one is sustained power consumptions. Here, sustained is, I mean, this metric they are referring to as thermal design power. Here, the thermal design power, it's all about determining the cooling requirement. Because I told you the how much power it consumes is not a matter nowadays. How much it dissipates, like what is the heat dissipation is the matter. So accordingly, right, we have to determine the cooling requirement. That is very important here. So this thermal design power is for determining the cooling requirement. It is nowhere related with the power, like what is that peak power that is needed, or like what is that average power. It is not that case. Okay, so typically, right, this is something a metric wherein right a typical power supply is usually tries to exceed the TDP. When you are going for power supply, you should have some TDP measures. That TDP, that is thermal design power, has to map with the power supply, wherein the total power supply has to exceed this TDP. And similarly, when you take a cooling system, it has to either match or exceed this thermal design power. So, which means, right, we need to determine this metric first. This TDP has to be determined, and accordingly, right, the power supply system and the cooling system has to be designed. So, power supply system has to be like it should be it should exit the TDP, and when you go with the cooling, either it should be matched or exit the TDP. And the next thing is, just when you go with the, if you are not providing the adequate cooling, so if you won't have a adequate cooling, so what will happen is, we will allow the junction temperature in the process to exceed its maximum value, which results in device failure and possibly some permanent damages is happened. So this what, if the heat dissipation is not carried out properly, it may lead to this. Okay. So voltage drop can be, listen here, voltage drop can be handled with respect to voltage indexing method. But when you just go with this cooling, if it is not handled properly, if the cooling is not handled properly, so probably results in device failure, and possibly that may be a permanent damage also. So we have to be very careful. So how it has to be done? How to manage the heat in modern processors? So they are going for two things. One is they have the circuitry which reduces the clock rate. So if the thermal temperature has been increased, so automatically so there may be some circuitry which reduces the clock rate, because here what is the clock rate? The speed at which the processor is running. So when the processor is running at speed, at that time only your heat gets dissipated. So obviously, if you are reducing the clock rate, what will happen? You understood the relationship or not? Okay. So when you are just increasing the clock rate, probably the power consumption will be increased. So when you are increasing, so clock rate increased, automatically power consumed will be increased. So parallelly, which will be increased? Heat dissipation. The heat dissipation will be increased. Can anyone say which will be decreased? So running the processor at maximum speed, which may be decreased. Anything is decreased? Hey, any people is there?
Yes, ma'am.
Yeah. Which is decreased?
Time.
Yeah, correct. Time of what? A task, isn't it? Good. So execution time of a task will be reduced. But if we are trying to do this, all will happen. So this will have a greater impact on heat dissipation. So probably they will start reduce the clock rate. So if you are reducing, so this also be reduced, and the power things will also be reduced. Or else they have some overload tripper is activated to power down the chip. So again maybe some component may be there, so it will be activated to power down the chip. Okay, so these are the two features that have been there in the modern processors to dissipate, to handle the heat. Okay, so one is the reducing the clock rate, another one is thermal overload tripper, and the third factor is the energy and energy efficiency. Okay, so this is the third factor, energy and the energy efficiency. So generally power is simply energy per unit time. So it is 1 watt equal to 1 joule per second. Because in general, energy is always a better metric because it is tied to a specific task and the time required for that task. Okay, so when you are just calculating, when you are just saying the time required for the task, it is almost we are just trying to compute the energy. Okay. So always the energy to execute a workload is equal to the average power times the execution time for the workload. Okay, so if you just ask the energy to execute the workload, it is equivalent to the execution time for the workload. Okay. Suppose for example, if you have this, a processor may have 20% higher average power consumption than processor B, but if A execute the task in 70% of the time, led by B. Okay, so if you want to evaluate the performance with respect to the energy of processor A and processor B, So here, right, the processor A have 20% higher average power. So probably, right, you have 120. So, but it tried to execute with 70% of the time. So, right, so 120, right, you have 1.2 into 0.7, it is 0.84. Energy consumption of A will be 0.84. So, I think, right, it is much better than the B. Because since it is average power consumption, probably right the processor speed will also be more and it may execute much faster than the B processor. So that's what they are trying to say here. And some general formulas they have given. Uh, one second. On, on, plan. Emergency button. Check. So next one is the energy and power within a microprocessor. I mean, how they are relating. I think this all. I mean, just remember these equations. The energy is like directly proportional to the capacitive load into voltage square. Because again, I'm saying people may. I mean, they may give some value, right, and they may ask you to solve these problems. So just kindly just note down all those formulas, be thorough with these formulas. And I mean, this equations is like a MGR pulse of the logic transition from 0 to 1 to 0 or 1 to 0 to 1. So you have like this, right? So from 0, sorry, from 0 to 1 to 0. So you may have this. Okay. So suppose like if you have only a single transition that is 0 to 1 or 1 to 0, then it is going to be half of the 1 by 2 of capacity load into voltage square. So this is the generic formula. So keep remember. So energy is directly proportional to the product of capacity load driven by the transistors and the square of the voltage. Okay. So here right, suppose we have yeah, here right, that is for the energy. And if you just take a power, so in case of power, it is one half of the capacity load into voltage square into frequency switch. So this is what this is the energy, isn't it? So this part is the energy. The previous things we are seeing. So this is the energy, and that into frequency switched will be uh, directly proportional to the power dynamic. So now, right, suppose if you have a problem, so you take this. So some microprocessors today are designed to have an adjustable voltage because we can adjust it accordingly. I mean, we have some features current we can able to adjust it. So a 15% reduction in voltage may result in a 15% reduction in frequency. So now the question is, what would be the impact on dynamic energy and on dynamic power? So if you are just reducing it, so what will happen if you are reducing by 15% in voltage and in 15% in frequencies? What will be the impact on dynamic energy and on dynamic power? So obviously, right, this is going to be the ratio, right? It's a ratio of the voltages. So we have right. So new, I mean, here the new energy is what? 15% reduction in the voltage. So what is that? It is in 0.85. Yeah, because we have already like assume like we have 100 voltage. So in that right, 15 voltage. So right, we will have like 85. I mean, when you just make it as percentage, like we have 0.85 voltage. Okay, so new energy is what? 0.85 voltage square divided by normal voltage square, because this 1 by 2 capacitive load will be cancelled for both the cases, energy new and energy volt. So the only thing is new voltage is 0.85 voltage square divided by the voltage square. So ultimately, right, you will get it 0.72. This is the ratio between the energy new and the energy volt. Similarly, right, when you just go with the power new and power old, so we know, right, just now we saw the formula is this is the energy into frequency switched into the same thing, right? Here also 15% reduction in frequencies for the new frequencies for the new, and that is divided by the volt. So again, right, you will get the value as I mean, you may get some value that divided by this. It is 0.61. Okay, sorry. So this is 0.61. So now what happened is, so shrinking the power to about 61% of the original. So when I just doing a reduction in voltage, like 15% or in frequency, so what is happening is power reduction, I mean it has been reduced to 61%. So you're clearly right. If you have a chance to reduce the voltage, well, just whenever you are running, if you have a chance to reduce the voltage or the frequency, so probably, right, the power consumptions may be reduced. Okay, so I mean just for that only this has been given. You understood or not? Okay, so during runtime, okay, we cannot fix it up because keep remember. I mean, if you take the desktop, normally, right, they will say 3 gigahertz. I mean, the processor speed, okay, the processor speed, they will say it as 3 gigahertz. Assume that it is going to be 3 gigahertz. Do you think that the processor will be executed in 3 gigahertz always? Will it be executed in 3 gigahertz?
No, ma'am.
All right. So, I mean, if you need just try to explore, there is some word called the frequency scaling. Because you yourself can do it. I mean, just if you're using a Linux operating system, you can very well do these things. You can try it out also. So we can fix it up at what rate you can execute your code. So say suppose if you have a 3 gigahertz, so some frequency scaling they will given like this. Okay, 800 kilohertz, 1200 kilohertz. Like this they may mention also. So 1 gigahertz. So 3 gigahertz. So I mean, various frequency rate they may give. So at which rate we want to execute, you can execute, and accordingly you can choose. Where it may be helpful. So assume that I'm executing a code. So let it be the deadline for executing. It may be like a 20 seconds. Within 20 seconds, it has to get executed. If I'm using 3 gigahertz, maybe right the code may be executed within 10 seconds. But 20 seconds is, I mean, I'm just giving a maximum time. 20 seconds is more than enough. If I'm executing the processor on 3 gigahertz, it may complete at 10 seconds. But actually, what is happening here? The power consumption will be more. The heat dissipation will be more. But what I can do? Maybe I can reduce the speed of the processor to 1 gigahertz. Thereby, right, I'm trying to reduce everything, right? The power required, all those things I'm reducing. At the same time, I'm meeting my requirements. Whereas I'm trying to execute my task within that deadline. So that's what. Okay. So if there is a possibility in that, it is there also. Not if suppose this possibility is there. You just try to explore frequency scaling. Okay. Wherein right, we can execute our task at multiple frequencies, and we can execute also. Okay, so here they are given if there is a 15% reduction in voltage and suppose 15% reduction in frequencies. So what about the power? How much power it may take? So right, we are just shrinking the power to about 61% of the original. So that's what. So this example says. And just the story here they given is suppose right. Like how about the power consumptions they take? When you go with the first microprocessor, it consumed only less than a watt. And then right when you just go with the 32-bit microprocessor, it's about 2 watts. So when it is 3.3 gigahertz Intel core, it consumes 130 watts. So this much of heat must be dissipated from a chip that is about 1.5 centimeter on a side. I mean the chip size, right? So this many size, I mean this many heat must be um, dissipated. So obviously, right, whenever you have a heat dissipation, probably right, the cooling has to also be reduced. And even nowadays, right, what to say? have you seen, like, I mean, when you're purchasing the desktop, the speed on this processor, right? This has been the research over increasing the speed of the processor has almost what to say absolute. So nowadays there is no more research is happening with respect to the speed. Even if you check, right from 2010 to 2020, if you just look onto the processor, almost all the processor is running with 3.3 gigahertz. Most of the processor, the maximum speed will be 3.3 gigahertz, and with some turbo optionality will be there. So there is no more research is carried out on the frequency speed, because it couldn't able to tolerate. Even if you go more beyond that, right? So probably the heat dissipations will be more, and whatever the circuit that are there to build up that chip, right? So it won't tolerate also. So like over a decade, I think the research over increasing the frequency has been stopped. If you want, you can verify also. I think here, here it has been given. See, I think this what it says, right? So it started from 525, 150, 500 megahertz, 1000 megahertz, 3 to 3. So I think after that, it started this. You have only the flat cases. There is no more research on this. I think with that speed we are doing it. Even with 2 megahertz, we don't know what we are doing it. I'm not joking. Most of the time, my laptop will be only 5% of CPU I'm using. How many of you have 100% CPU? You say, does anybody saw that in your processors? I mean, when you open this processor usage.
Yes, ma'am.
While gaming, and
Yes, yes, ma'am.
yeah, remove those two those two applications. Other than that, if while executing my Python code or C code, it's using my processor. Do you say that? Since I'm not using, I'm not playing any games in my laptop. I couldn't able to see.
Occasionally, ma'am.
Occasionally, maybe infinite loop. Okay. Okay. So they have given some modern techniques to improve this energy efficiency. Of that, right, do nothing. So it's a good thing, right? So suppose, right, if you're not doing anything, probably, right, we need to turn off the clock of the inactive models, because even if you're not using it, so there may be little power consumptions will be there. Okay, so that's why, right, now I don't know, when you go much deeper into that, there they will say, okay, in running mode this much power will be consumed, in idle mode this will be in start, so many modes will be there. So it depends upon the scenario, how many power consumed. Like this they may mention it when you're just going for purchasing, even if your memory device some things. So they will specify this many amount of powers will be consumed in these kinds of modes. It won't be like a single power consumptions. So they will give variety of modes and something will be there. So accordingly, right, we need to make use of those modes. So if you're not doing anything, it has to be immediately turn off. So even, right, the one such example is a floating point unit. You don't, when you talk as an ALU, even when you are read about what is that? Digital circuits, we haven't to think about the floating point operations. We just know what is floating point numbers, but you haven't come across with this while designing an ALU, because when you go with normal ALU, it will be capable to work only with the integers. You have a separate floating point unit and it will be communicated with this. And it is not the case, right, all the time the floating point unit may be in use. So at the time, right, we need to disable the clock of the floating point unit when there is no FP instructions executed. So while because the compiler will do everything, because we are not worrying about because if we do this float A B, so probably, right, suppose A B C something, if we are doing C equal to A plus B, while compiler is converting this code, so clearly, right, it will convert to the floating point instructions. So only those cases it will goes to the floating point unit. So the rest of the cases it will disable. So this what, when it is not in use, so we can turn off the clock. This yeah, here it is. The next one is the dynamic voltage frequency scaling. This is what I told you, right? DVFS. We just please explore this. this is the technique for reducing the dynamic power consumption by dynamically adjusting the voltage and the frequency of the CPU. So you can clearly try in Linux. So at least write one example. You just put your C code and you just try it running at various frequency and just check out how well the power consumption is happening. Okay, so okay, this DVFS and this is for typical case, and it is what I mean depends upon the devices. We have to take care of it. So memory and storage offer low power modes to save energy when PMD and laptops are idle. So this what the DRAM have a series of increasingly low power modes to extend the battery life in PMDs and laptops. Similarly, when you just take a disk that may spin at lower rates when idle to save the power. So I mean, just it keeps spinning, right? When it is in idle, so at lower rate it may spins. Similarly, when it is going for read, so it has to comes to the active mode. And the suggestion they are given is on-chip temperature sensor to reduce the activity automatically avoids overheating of the processors. So I mean, this what is important. Okay. So if suppose if you have an on-chip temperature sensor, probably right. It may check out the heat dissipations and accordingly, right, it may avoid many things because this is very important thing. And even nowadays, right, we are very much aware of that, right? So when you're running our own laptops, we don't know sometimes it may get heated. So I mean I am very much aware on that. That's it. Dean. Oh no. Call for it. So you have to be very careful, right? Suppose if you have very much heat dissipations, so try to take care of all those things. Okay. The next one is overclocking. This one I told you, right? Turbo mode. Suppose if you are just working in, I mean, if the processor is like 3.3, some hardware technology, right? You can go like 3.6. So we can meet out that. But right, we can do that until the temperatures start to rise. Just like that, we cannot run it out. So until the temperatures start to rise, we can run it out, and accordingly we have to move it up. So that is important. Though we are just going for the turbo, so again, right, we need to take care of those things. Okay. So these are the 4 cases for what to say efficiency, energy efficiency. One is do nothing well. Next one is the dynamic voltage frequency scaling, and the design for typical case and for overclocking. Okay. So okay, with respect to this topic, let me just brief out like trends in power and energy. So first has to be brought in, and the next it has to be, I mean, the power dissipation has to be handled properly. So 3 primary concerns. When you just go for the power and energy cases, 3 primary concerns. So first we have to think about the maximum power that needs required, or else it may lead to a voltage drop. The next one is the power consumption, sustained power consumptions, wherein right we need to design a metric called thermal design power. So it is not like a peak power or like a average cases. Okay, some metric wherein power supply system and the cooling has to get coincide with that. That's it. Okay. Suppose if the cooling is not good, so definitely it may result in device failure and it may lead to permanent change. And so when you want to manage the heat, 2 things is, one is right, we need to reduce the clock rate, or else you should have some thermal overload tripper to take care of that. And the third thing is the energy and energy efficiency. So I think some formulas I have listed out. Yeah, please kindly go through these formulas. They may ask some problem on this also. So this kind of problems. So don't think that it is going to be tedious. Only just they will change the number. So instead of 15%, they make you 30%. So you must be in a position to calculate all those things. That's all. Okay. And this is what I told you, right? The clock frequency, the growth in clock frequency has almost like absolute out. So there is no more research on increasing the frequency rate. And to improve the energy efficiencies, these things, 4 things. One is do nothing well, dynamic voltage frequencies, design for typical phase, and the overclocking. Okay, so these are the 4 cases. So I think that this topic is over. Shall I continue? Guys, are you people are there or gone for lunch?
There, ma'am.
Yeah. Shall I? Or tomorrow? Last one.
Tomorrow, ma'am.
But again tomorrow, this another half an hour I will take it out. Okay. I will try to complete this first chapter. Okay, wow. Do you agree that? Because tomorrow second hour your break is there, na? So at that time, in that time I will continue. Okay.
Third hour we have a class, ma'am.
So no problem. Third hour will start at 11 o'clock, right?
Yes, ma'am.
I will continue till till 11. I will leave you at 11. Okay, wow.
Okay, ma'am.
Ma'am, if you conduct any test, please inform before, ma'am.
Yes, ma'am. Definitely I will do it, ma'am. No surprise test, ma'am.
Okay, ma'am. Thank you.
Okay, guys, I will post these 2 sessions today. Today's sessions on our Google Classroom. You just kindly check on. Thank you, guys. Thank you.
Thank you, ma'am.